Welcome back to lesson 4 of rates of reaction. Mr. Hutton here, just taking you through this lesson 4 for rates, which is on temperature and the effect temperature. So resources available to students at school. These are what we've got. They're your book pages if you need them, and if you've got the revision guides, the pages are there to help you as well. So as always, there's a little starter here, so how the pictures link to the lesson. So have a quick go, pause the video, just have a go and see what you can come up with. Alright, so top left, a picture that you might see in physics as well. So there's a thermogram, so a thermal image of a house showing you how the temperature changes on a house. What you don't want to see, in fact, what you don't want to see here is lots of heat on the roof, because that would be heat loss through the house. So this house looks like it's quite well insulated, although those windows don't look to be particularly good. Alright, what else do we have? So the next picture along, so we've got a graph in the middle there with T1 and T2. So T1 and T2 are temperature 1 and temperature 2. And what you can see, by changing the temperature, we can change the number of particles that actually have exceeded the activation energy. So the red line there, okay, that's actually a lower temperature, because the y-axis there is your number of molecules. It's not actually a temperature graph. It's the number of molecules. So the red line, and you can see that red block, there's a small proportion of particles that have exceeded activation energy, whereas the blue line, okay, the curve flattens a bit because we can't change the number of particles, so the volume under the curve is staying the same, but there's a greater proportion of them have shifted over to the right and have got the activation energy. So the top right graph, we've got two lines there at different temperatures. Oddly, the higher temperature has the blue line and the lower temperature has the red line. That goes against what you'd expect. So you do have to look out for that in questions and exams. And that blue line, the 100 degrees Celsius, you can see is much steeper. So it's a faster rate of reaction. Remember, our gradient tells us our rate of reaction, so the change in y over the change in x. And the other line at 78 degrees, I think it is a flatter line, not as steep, so the rate of reaction isn't as high. We've got an image of an apple, and it's slowly oxidizing. Okay, so the browning of the fruit there, that is an oxidation reaction, so it's reacting with the oxygen in the air. And quite often what you do, or what your parents might do, is if there's bits of fruit that are uneaten, they might put them in the fridge. Okay, so a colder space where we slow the rate of reaction. And there's a storage label there for some kind of food. It says to keep refrigerated once opened. So again, this is the reason we put things in the fridge, is to slow the rate of reaction they're having with oxygen that normally makes them go off. We're trying to slow that down. And putting things in the freezer, you're really trying to stop reactions altogether. Right, so this is what the AQA specification says. Pause it if you want to look at that in more detail. And again, in a lesson at school, we'd go through these objectives a bit more. We spend a bit more time on it, but just pause the video just to read through those now. Alright, so what do we know already? So from previous lessons now, you should be able to answer this. Do all particle collisions lead to a reaction? No. Good. Particles need to collide with enough energy, the activation energy, and they need to collide with the correct orientation. Right, the rate of reaction. What two things are affecting rate? So remember how frequently particles collide and the energy with which particles collide. So these are the two things that we can have an impact on to affect rate. Okay, so we can affect how frequently they collide. So with surface area, by making the surface area bigger, we made the frequency of collisions much higher, which increased the rate of reaction. With surface area, we didn't affect how much energy the particles had, right? But when we look at temperature, okay, then what we will be doing will be affecting both of these things. We'll be affecting how frequently the collisions occur, and then also the speed at which the collisions occur. So how does temperature affect rate of reaction? So this is the same graph that we saw in the starter. So just have a quick look at that, pause the video and describe how the temperature affects the rate of reaction. Good, the higher temperature, the faster the rate of reaction. The 100 degrees Celsius line is much steeper than the 75 degrees Celsius line. Remember, rate is represented by the gradient, and we work that out by the change in our y-axis over the change in our x-axis. But why does an increased temperature give us an increased rate of reaction? So remember, when we think about rate of reaction, the two things that we're trying to influence is the frequency of collisions and then also the energy of those collisions. So how does increasing temperature affect the frequency, and also how does it affect the speed of those collisions? So just have a think about that now and pause the video. Good, so there's going to be two things we're looking at here. The first one, the particles have more energy at higher temperatures. So that means they're moving around a lot faster. So therefore, they're going to collide more frequently. If you imagine a room of students, okay, and you're moving around slowly, okay, you're not going to bump into each other that often. But if you're all moving around really, really quickly, you're going to collide much more frequently. Okay, so the higher temperature means the particles are moving faster, which means they will collide more frequently. Right, the second point, okay, is very similar, but there's a little difference at the end. So the particles, again, they have higher energy, more energy at the higher temperatures, so they're moving faster. So therefore, the proportion of those particles with the activation energy is actually higher. So not only are they colliding more frequently, but they're colliding with a higher speed. More of them have got the activation energy, so more of those collisions will actually lead to a reaction. Okay, so there's two different things there that you would need to mention in an exam. You need to talk about how the temperature means the particles move faster, so they will collide more frequently, but also that a higher proportion of those collisions will have the activation energy. As a general rule of thumb, okay, a rise in temperature of 10 degrees Celsius will cause the rate of reaction to approximately double. Okay, that is a very general rule, but it can be applied quite frequently to reactions. All right, so what we're going to do, we're just going to talk about a practical that you would have done at school, or there are videos of this online that you can find. But we'll just talk it through, and hopefully you'll get a sense of what would have happened. So the reaction between sodium thiosulfate, okay, that's probably a new thing you've not heard of. That doesn't matter. We're just using this for this because it demonstrates our point quite well. Okay, so sodium thiosulfate and hydrochloric acid produces sulfur. The sulfur would be a solid in this case. So think back, I think it was the first lesson on measuring rates. Okay, we talked about what we call a solid that is formed in a reaction between two solutions. Okay, so just pause the video for a moment and see if you can remember what that was. Precipitate, good. So when we have a reaction between two solutions and it forms an insoluble solid, that is called a precipitate. And the reaction between sodium thiosulfate and hydrochloric acid produces sulfur, and the sulfur is an insoluble solid at this point, so it is a precipitate. So here's an example of a word equation and a symbol equation for that reaction. So sodium thiosulfate plus hydrochloric acid reacts to give us sodium chloride plus sulfur dioxide plus sulfur plus water. And you can see in the symbol reaction that we've got the state symbols below our reactants there. So they're both aqueous, so they're both solutions. And then in the products, you can see how we actually get an aqueous solution of sodium chloride, sulfur dioxide gas given off, the sulfur as a solid, so that's our precipitate, and then water as a liquid. As sulfur is a solid, what would you expect to happen to the solution? So again, we talked about this in the first video when one of the ways of measuring rate of reaction. Good, it turns cloudy. Okay, so as that solid precipitate is formed, the solution will go cloudy. So then, how can we use this phenomenon of it going cloudy? How could we use that to measure the rate of reaction? Good. Hopefully you've come up with this idea of using the black cross, all right, on a piece of card with your conical flask over the top, looking down into it, and as that sulfur is produced, it becomes more and more cloudy, and then when you can't see the cross anymore, you would stop your timer, all right? So an example there, it would start off very clear, and then at the end you cannot see the cross through the solution because of your sulfur precipitate. So you're going to measure the time it takes for the cross to disappear at different temperatures. So what you would do is you would change the temperature of your reactants. So you could have some that had been in the fridge, you could have some at room temperature, and then you could have some that had been in a water bath. So your reactants are at different temperatures. And then as you pour them in together, you start your stopwatch, and you'd probably swirl it round a little bit, and then as soon as you couldn't see the cross anymore, you're going to stop that stopwatch and measure the time. All right, and hopefully what you'd see is that the reactants that you had at a higher temperature in the water bath, you'd have a much quicker time for that sulfur to be produced and make the solution go cloudy than the ones from the fridge that are going to be reacting more slowly because the particles aren't moving as quickly, so they're not colliding as frequently, and those collisions won't have the activation energy either. Okay, so remember, we need to be talking about the frequency of collisions and whether those collisions have the activation energy or not. Right, so thinking back to that first lesson we did on measuring rates, what other ways are there that we could measure rate of reaction? Just think back now and see if you can remember. Good, so hopefully you've come up with these. Measuring the volume of gas, that was the first one we looked at in that first lesson, and there's two ways to do that. You could have your gas syringe on the left there, or you could have the gas coming through into an upturned measuring cylinder. What we've just looked at the bottom there is measuring the time taken for a cross to disappear, so as a precipitate forms, or you could also just measure the decreasing mass of a reaction vessel as a gas was produced and it left the reaction vessel into the atmosphere. So that brings us to an end of today's lesson on temperature. So the important things to remember there in terms of how temperature affects rate of reaction. Increasing temperature will increase rate of reaction. The reason it does this is because the particles have more energy, they're moving around more quickly, so they will collide more frequently, and also a higher proportion of those collisions will have the activation energy. Thanks for listening, guys. I hope you're subscribing and you've enjoyed these videos so far. The next one we've got coming up is on concentration and pressure. There's a required practical element to that as well, so you will need to just maybe brush up on that before you come to that lesson.